Hello and welcome to the Terran Space Academy. As I write this, the Starship is preparing for its first suborbital flight. The heat tiles have been placed, the engines are being tested, and soon, if all goes well, it will launch itself into space. It will not go into orbit, though it will generate enough delta V to easily do so. It will instead be fired into a ballistic trajectory. The Starship will travel most of the way around the world, and then bring itself down near the Hawaiian Islands. If the booster survives off the launch pedestal, the mission will be a success. If the Starship system survives to separation, it will be a triumph of engineering, technology, and the human will. If Starship survives to re-entry, even if it fails to survive the heat of re-entry, SpaceX can immediately start planning on orbital Starship stations, or as I like to call them, StarLabs. I recently watched an excellent lesson on Roman history from this new channel created by my friend Sebastian. If you love history, this is a great place to learn. While I know a little about the Roman Empire, up to Marcus Aurelius, I didn't spend much time on the fall that came after. It saddens me to think of what humanity lost. Progress is not inevitable. We know that in the past, progress has not just stagnated, but regressed, leaving us in a dark age. Humans have now been in a space capability dark age for almost exactly a half-century. The Saturn V was, and still is, the most powerful rocket to ever fly. It could lift 140 metric tons to low Earth orbit. Let's get some perspective. The Falcon 9, when expendable, can lift 23 tons, the same as a Proton M, and just a little less than the Space Shuttle, which could lift 27 tons. If the Vulcan ever flies, it will lift 35 tons. The New Glenn 45, and that's impressive, but the Falcon Heavy can already lift 64 tons. The SLS will be able to lift 95 tons, and the failed Soviet N-1 moon rocket would have been 95 tons also. But though the Soviets failed with the N-1, they succeeded with something even better. The Energia rocket system the Soviets built and flew only twice could lift 100 tons. Starship will lift at least 100 tons and be reusable, but perhaps as much as 150 tons. Only if Starship succeeds at lifting 150 tons to low Earth orbit will we have surpassed our grandparents' generation. Think about that for a moment, and where we could be had we kept improving on Apollo technology in the 70s. An orbital human habitat in space is called a space station. Permanent homes in orbit had been dreamed of for centuries. Edward Hale wrote of making one out of bricks. Not very practical, but it's the thought that counts. The first to envision a rotating space station was Konstantin Tsiolkovsky. Werner von Braun popularized the concept with the help of Walt Disney. The first space station would be launched by the Soviets and called Salyut 1. Then came Almaz, a Soviet military station, and later Mir. Today, orbiting above us right now, we have the International Space Station and Tiangong. The International Space Station was built mostly by the United States and Russia. The Soviet Union had collapsed by then, but all their technical expertise was not lost. If you are unfamiliar with the triumphs of the former Soviet Union, watch this lesson. But China was excluded from participation. Over the years, China saw the ISS grow to be the largest thing ever put in orbit. The Chinese got tired of watching and decided to build their own. To catch up on the Chinese space program, we have this lesson. The Chinese started with just one module, with plans to expand it. But we are not here to talk about small stations, built one module at a time. We are here to learn about the largest object ever placed in orbit so far, and dream of the day when that record will be broken. The Saturn V had an RP-1 or kerosene first stage. The first stage needs power as much as efficiency to get the rest of the rocket above the atmosphere, so it can go on into orbit. The Saturn V rocket had a total mass of about 2,926 tons. The first stage of the Saturn V had a dry mass of 130 tons, and a propellant mass of 2,160 tons. It had a specific impulse of 263 seconds, and after burning all that RP-1, the rocket had 3,458 meters per second of delta V. But at first stage burnout, it was just 61 kilometers from the ground. 74% of the rocket's mass had been expended just to get here. The second stage of the Saturn V was hydrogen-powered, and now that it was above over 99% of the atmosphere, didn't have to worry about atmospheric drag. There is a deep dive into the second stage in this lesson. The second stage burned its 456.1 tons of hydrolox propellant. The hydrogen-powered engines had a specific impulse of 421 seconds. And at second stage burnout, the Saturn V had developed another 5,219 meters per second of delta V. That brings us up to 8,677 meters per second delta V. Almost the 9,400 needed to get into orbit. The third stage of the Saturn V was also hydrogen-powered. It would develop another 6,122 meters per second of delta V, getting the Apollo Command Module, Service Module, and Lunar Module up to 14,799 meters per second of delta V. Enough to get to the moon. But as the Apollo missions were winding down, the scientists decided to do something different with the last Saturn V to launch. They decided to launch a massive space station. Skylab was built from a Saturn V third stage. After second stage burnout and separation, the third stage had a delta V of 8,677 meters per second. With just another 723 seconds of delta V, the third stage can go into a low Earth orbit. But Skylab had a total mass of only 76.54 tons, not the 123 tons of the usual propellant-filled three-stage. When we put that new mass into our equations, the Saturn V after third stage separation has a delta V of 9,720 meters per second, more than enough to reach an orbit of 455 kilometers. Once in orbit, the Skylab had about 350 cubic meters of pressurized volume in one launch. The International Space Station was started in 1998, with the Zarya module launched on a Proton rocket. Over the next 13 years, more modules were added, until today, after almost 25 years, $150 billion, and a total of 40 launches. The ISS has a pressurized volume of 932 cubic meters, if we add in the Bigelow Expandable Activity Module. But it only has 388 cubic meters of habitable volume. Each Skylab was 352 cubic meters of habitable volume. If every Saturn V Skylab launch cost $1.5 billion, we could have had a station in orbit 10 times the usable volume, with only 12 launches, and saved ourselves about $132 billion. We could easily have 100 people living in space since the 1970s, and money left over for a moon base and a Mars mission. Skylab was in orbit for 6 years. During this time, they did hundreds of experiments. One researcher won the Nobel Prize for his work in X-ray astronomy. NASA had expected Skylab to stay in orbit for 9 years, and the space shuttle was supposed to be ready in plenty of time to boost it back to a safe orbit. But its orbit decayed faster than they expected, and the shuttle took longer than expected to fly. Skylab could not be saved, and after 4 manned missions, it burned up over Australia. Australia is a big, sparsely populated country, and no one was injured, but that was the last Apollo Saturn V flight. Several of these rockets are on display, like the last Energia that was stored away. But sadly, these giants of human ingenuity will never fly again. But if all goes well, sometime this year, a Starship with 1,000 cubic meters of pressurized volume, much more than Skylab and the ISS combined, will launch into orbit. Once in orbit, SpaceX can bring up the crew with a Dragon capsule, already human-rated, and keep it docked as a lifeboat, should anything go wrong. Even if NASA limits SpaceX to 5 launches the first year of Starbase operation, there can be 5 StarLabs orbiting the Earth by the end of 2022. Research organizations can lease space on the StarLabs to work on advanced fiber optics or 3D printed human organs, and run centrifuge tests on the effects of Martian and lunar gravity. This can help offset the cost of development. Once a ship has been in orbit for 18 months, we will have proven it can survive the journey to and from Mars. While in orbit, the life support and power systems can be perfected. When a StarLab is decommissioned, it comes back to land, testing the heat shield after an extended stay in space. As more launches are authorized to refuel, some can be sent around the Moon and others to orbit Venus, with large crews to deploy probes and perform science and industrial experiments. Eventually, star factories will be placed in orbit by different companies, solely for the production of high-value products that can only be made in space. As soon as 2024, we could have learned enough to send one to Mars and try an uncrewed landing there. If we can get a fuel refinery on the surface of Mars, we'll be opening the door to settling the planet. Something to think about. Thanks for listening. Please don't forget to like and subscribe, and stay safe at Astra Pro Terra.